Hello students, so this is a summary of what has been discussed today in the HTM class. So we have mainly discussed about the eutectoid transformation in the iron carbon phase diagram. Now you can see that this is the eutectoid transformation that is taking place. So the austenitic phase is getting converted into two solid phases. One is the alpha, the ferrite and the cementite. Okay. And this takes place around 727 degrees centigrade, and the carbon concentration at the this position, exactly this position, is 0.8 percentage of carbon, and this corresponds to the phase pearlite where you are having a lamellar structure. Now, if we look into this region of the diagram, what we can see that with an increase in temperature, the iron changes its phase. That means for a fixed concentration of carbon, if the temperature is increased, the alpha phase of of iron is getting converted into the gamma phase. So there is a phase transformation going on at a particular carbon weight percentage, but with increase in temperature. Now, the reason why this change in transformation occurs is due to the nucleation of phases. I mean, if there is, this is how the alpha microstructure looks like. Now, at this position, if we are increasing the temperature, although we are not supplying any extra source of carbon, simply because of increased diffusivity of the carbon into the gamma phase, the formation of gamma, that is austenite, takes place, and also due to incorporation of more carbon, the austenitic phase is harder compared to the ferrite phase. Now, the ferritic phase is a BCC structure, and the austenitic phase is an FCC structure. Now, since they have different atomic pattern fraction, so there is more space available in the case of FCC, which is the reason of more carbon diffusion. Rather, we can say that the FCC phase in the form of austenite can hold more carbon compared to the ferritic phase, and this gives rise to the hardness. So, what we can infer here is that somehow, due to incorporation of this carbon, the hardness of the phase formed has increased. So, now carbon, as you know, comes in two different forms. In normally allotropes, there is diamond and there is a graphite. Now, this diamond is mainly sp3 hybridized, whereas graphite is mainly sp2 hybridized. That means mainly carbon-carbon single bond is present in diamond, whereas sp2 consists of carbon-carbon, mostly carbon-carbon double bond. Now, graphite is the most stable phase of carbon. Now, if we take a graphite and it is considered to be a layered structure, so you can see this is a graphite, the lines that represent are the different layers. Now, at this point, if we take a scotch tape and we paste it and we lift it, and there is some carbon from graphite being transferred to the scotch tape. Now, this region where the new carbon materials have stuck, this is basically taking out few layers of carbon or few layers of graphite with the scotch tape, and this actually gives rise to a new type of material which is called graphene. Okay. Now, so we have graphite, we have diamond, we have graphene, and we also do have some amorphous materials where all types of hybridization sp2, sp, and sp3 may coexist. So that is the amorphous phase. So there are different phases of carbon or carbon existing in different phases apart from this sp2 graphite and sp3 diamond. So this has been represented in this phase diagram, which is showing the different phases of carbon. And so at the two extremes you have sp2, which represents graphite, and this is sp3, which represents the diamond. And there is formation of other phases. This position, this vertex is that for hydrogen, because CH, for any organic material, CH is the most significant bonding. So we are not concentrating on the hydrogen phase. We are mainly concentrating on the carbon phase. Now, carbon, as previously told, can exist in amorphous phase also, and sputtered carbon, they are usually in the form of amorphous carbon, whereas as the tetragonality of the phase increases, that means from amorphous carbon, some of the carbons they form tetragonal phase carbon. They start to crystallize, and ultimately all the amorphous carbon has been observed in crystallizing the material. It forms sp3 carbon, which is basically diamond. Now, Raman spectra is one of the molecular spectra which is used in mainly determination of carbon phases. Okay. Now, what has been formed is before going into the details, it has been assumed that the molecule that is being considered for making for the theoretical aspect is a rigid rotator molecule. That means two atoms are vibrating, and there is a rigid rotation going on. Okay, they are rotating, but they are not vibrating. So with this concept, we developed a spectroscopy which is associated with the rotation of the molecule, that is called microwave spectroscopy. And there are different moment of inertias, like I have represented them as A, B, C. One will be along the axis, one will be perpendicular to the axis, and one will be in a perpendicular direction at 90 degrees to the axis. So there are three moments of inertia. Based upon three moments of inertia, we can have different cases and we can have different energy levels. So this goes for the rotation, which coincides with the microwave spectra, and microwave spectroscopy holds for these molecules. Now, apart from that, there is also effect of temperature on rigid rotator molecule. Molecule will tends to vibrate, and so if we plot the energy versus the distance diagram, it looks something like this, with the different vibration states formed, and after a certain stretch, the molecules break up. So that amount of energy is the dissociation energy. Okay. Now, as we have previously told, by taking few layers of carbon from the graphite, we form the graphene. Now, the graphene number of layers should be less than 10 usually, because if it is more than 10, it again catches up with the graphitic properties. So this graphene again, if we take one single monolayer, one single top atomic layer of a graphite or a graphene for that matter, if we take and we can divide it into different chiral vectors. Chiral means to roll. So we have set up a coordinate system by taking any carbon as the origin, and we have developed a coordinates 2D coordinate systems A, B, and so there are different chiral vectors associated with which are represented in terms of the basic vectors A and B. Now the chiral vector along the a-axis. That means if we roll this graphene sheet along the a-axis, and we can also roll it at a 45-degree angle to this a-axis. So in both the cases there will be a chirality generated. So in this case M should be equal to n, since it is in this diagonal directions, and here the x component should be there. There won't be any y component. That means it will be m any value or 0. Okay. Now, if we roll it either in this direction or in this direction, we get two different types of carbon nanotubes. So now we are dealing with carbon nanotubes. There are two different types. One is this one, which is called an armchair. This type of carbon nanotube will be obtained if we roll it along this direction, and if we roll it around the other direction, we get a zigzag pattern. Now, coming back to the Raman spectra of carbon, any carbon-related material, if we perform the Raman spectra, will get two peaks, basic fundamental peaks. One is called the disordered peak, and it is around 1320 centimeter, or might be some differences based upon the material. And then we have the normal graphitic peak, which is above 1500 centimeter inwards. Now, these peaks are due to two different motions. One is the stretching motion, as you can see with the arrows, the hexagon is stretching itself, and so this corresponds to this G peak, and the other one is the T peak due to the breathing property. So whenever we are having a spectra, the spectra of any carbon matter, it must have these two peaks. Like here you can see there is a G peak and there is a G peak. However, their positions as well as their intensity is depending upon what type of crystallinity or what type of crystals have been formed, right? So if there is more number of clustering, as you can see from the diagram, this D peak is supposed to go high in intensity. Okay, if there is clustering, the separation between D and G will increase, so on and so forth. Now, there should be a calibration chart, or there should be some rules by which, general rules by which we can identify what type of phase has been formed. So that rule was given by taking two different parameters. One is the G peak position, and secondly the intensity ratios of the ID and the D and G plots. So based upon these two parameters, Faraday and Robertson, they staged a three-stage model. As you can see, there is ID by IG ratio here, and there is G peak position here, and this curve is called the amorphization curve. That means it starts from sp2 carbon, it goes down in size, that means from graphite to nanocrystalline graphite, then from there it goes to amorphous carbon, and lastly it goes to tetrahedral amorphous carbon, that is the diamond like. Okay, so any Raman spectra, if you find out these two parameters, and if you could calibrate with this three-stage model, you can say in what condition my carbon crystals are without looking into the microscope. Okay, so that's it.